we're going to talk about 1.2 in your book. It's called The Basics of Functions and Their Graphs. The objective 1, there are 9 different objectives that we'll be covering in this section. The first objective is to find the domain and range of a relation. So the first thing we're going to talk about is the definition of a relation. A relation is any set of ordered pairs. So here in example 1, if I have just a set of ordered pairs, so the first thing is a ball, and the second thing I write here is red, and then I have a top, and I write that that's blue, and I have a doll, and it's pink. So this is a relation because in a relation, it's just a set of ordered pairs. I've just got two things that are connected together somehow. The set of all the first components is called the domain. So in this case, the domain of this set that I have come up with, and remember these curly braces that we have here are the things that denote that to be a set. This means this denotes set. Okay, it's called set notation. And so the domain here for this particular set of ordered pairs, or this particular relation is ball, top, and doll. And the range, which is just the second component of the ordered pairs, would be red, blue, and pink. And again, in the curly braces to show that that is a set, because the domain is a subset of the relation and the range is a subset of the relation. So when you are given a set, whether it's numbers or things, just remember if they want the domain, it's the things that are the first part of the ordered pair. The range are the things that are the second part of the ordered pair. So now I'd like for you in your books, on page 114, I want you to look at checkpoint 1. And write down the domain and range of the relation. So you'll need to pause the video and do that. Okay, next we're going to do objective 2. We're going to talk about how to determine whether or not that a relation is actually a function. The definition of a function, if you'll remember from Algebra 2, is that it's some kind of correspondence from a first set called the domain to a second set. In other words, it's an ordered pair again. But this set of ordered pairs is set up so that every element in the domain, that's the first set, has exactly one element in the range. So here, for our example, let's say that let's just go ahead and use a set of ordered pairs because I don't feel like writing all that stuff out. So I've got the numbers, the set 0, 1, and 1, 2, and 3, 0, and 4, 5. Okay. One of the easiest ways sometimes to be able to look at this is if you go ahead and set yourself up a mapping, and we'll go ahead and put our domain, which remember is just a set of our first coordinates, so that's 0, 1, 3, and 4. And then here we've got our range, and the second things are 1, 2, 0, and 5. And then you map these, so from 0 I went to 1, from 1 I went to 2, from 3 I went to 0, and from 4 I went to 5. So there's no place where one of these things in the domain went to more than one thing in the range. So this one is a function. But let's say that, let's give you an example of one that's not a function. So example 2, part B. Let's say my set of ordered pairs contain the points 1, 2, negative 1, 3, 1, 0, and 2, 5. Okay, so here's my set. Now if you do your mapping this time in your domain, You've got 1, -1. You don't need to write the 1 down again, and 2. And here you have your set, that's your range. And you got 2, 3, 0, and 5. So 1 went to 2, -1 went to 3, 1 went to 0 also, and 2 went to 5. So see here, our problem is that 1 is mapped to 2 and to 0 both at the same time. So this is definitely not a function. Okay. So now I'd like for you to look on page 116 and look at checkpoint 2. Go ahead and answer that on your piece of paper that you have. Objective 3 that's in this section says we want to determine whether an equation represents a function. And when we do that, remember that we are an equation would be something like y is equal to 2x squared plus 3x minus 4. Let's say that's my equation. Solve for y. If it's solved for y and the x is over on the other side, then my independent variable here would be the x's, and my dependent variable would be my y. Okay? You can take any value for x and substitute it in, and you can get something out of that equation and get a y from it. So that's why the x is from the domain. We just assign things to it, and then our result that we get from doing that, putting it into that equation, is where y would be. So that makes it our dependent variable. Now, just like not every set of ordered pairs gives us a function, not every equation gives us a function. And so the only way this works is that if we solve any equation that we have for y, if we can get more than one y value out of it, out of any x, then we absolutely do not have a function. So let's look at example 3, part A. We have x squared plus y is equal to 4. Now let's solve this for y. So solving that for y, we get subtract the minus x squared from both sides. So we get y is equal to a negative x squared plus 4. So if I put a value in for x, how many different y values can I get back for that? Okay, there's only one, because we're only going to get one y value back here. So this one is definitely a function. Now, part B on this one, let's give you one that's not a function. Let's look at x squared plus y squared is equal to 4. Now, again, I'm going to subtract the x squared from both sides. So if I get y squared is equal to negative x squared plus 4, the difference here this time is that that's not solved for y. To be able to get this solved for y, I've actually got to take the square root of both sides. And when I take the square root of both sides, remember that I have to take the positive and negative value possibility on one or the other. So look what's going to happen here. When I put a number in for x, I'm going to get a positive square root, but I'm also going to get a negative square root of that answer. So this one is not a function. So that's how you think about that. If you have to take the square root to be able to solve it for y, then it's not going to be a function. Now on page 117, pause for a moment and do checkpoint 3 to make sure you understand that idea. Okay. Now we've got objective 4. Objective 4 is talking about how to evaluate a function. And we need function notation here. Remember, f of x represents the value of the function at the number x. So in other words, f of x is really the same thing as the y that we've always had before. F of x is the value of that second piece of our ordered pair. So in this case, when I have a function that's maybe f of x is equal to, I don't know, 1.4 x squared minus 0.06 x plus 3. Then x is our input, for our independent variable. And f of x is our output, which means it's our result, so that is our dependent. It's not really a variable, but that is our dependent quantity. So the way this works is that if you have a function, let's say our f of x, let's look at a, f of x is equal to x squared plus 3x plus 5. And I want f of 2. Then the way you do that is, see how the x is replaced with the 2 on the left side of the equation? Then everywhere there's an x over here, I want to replace it with a 2 also. So that I get that this is 4 plus 6 plus 5. So f of 2 is equal to 15. So that ordered pair is the number 2, or it's the set, 2, 15, because 2 is the x value, 15 is the result that we get back from that. Now when you evaluate functions, many times you don't just evaluate numbers, sometimes you evaluate expressions. So on part B on that example, they want us to find f of x plus 4. Well, if I'm looking for f of x plus 4, that means I've got to take where the x is in x squared and replace that with x plus 4, so it's x plus 4 squared, plus 3 times x plus 4 plus 5. So remembering that our function originally was f of x is equal to x squared plus 3x plus 5, then you can see what we've done is everywhere there was an x, we just put in x plus 4, because that's what function notation tells us to do, is to replace the x with whatever's inside there that's our independent value. And then you just go through here and actually do the algebra to work this out. X plus 4 squared, remember, means x plus 4 times x plus 4. And 3 times x plus 4, remember, I can do the distributive property and get 3x plus 12. And I've got plus 5 just hanging on out there, don't forget it. And so now doing the full, I've got x squared plus 4x plus another 4x plus 16. And then I've got my plus my 3x plus 12 and 5 is 17. And so then combining like terms, I get x squared plus 4 plus 4 plus 3 would still be 11x. And 16 plus 17 would give me plus 33. Okay, so there's our result there. So now why don't you try to do that on your own. If you'll look on page 119, try to do checkpoint 4. Now, on checkpoint 5, what we're doing is we are taking the objective, not checkpoint 5, but the objective 5 is we're graphing functions by plotting points. The graph of a function is the graph of its ordered pairs. So we just have lots of different things that we could do here. Let's f of x is equal to 2x plus 3. Okay, here's our function in function notation. So if we were going to do this, remember that we can either we can make ourselves a table of values. So here's x and here's the f of x or y. And I can just put some different values in for x, or you can put it in your graphing calculator and look at the table, however you want to get these numbers. So let's just do -2, -1, 0, 1, and 2. And then if I evaluate that, then I get -1, 1, 3, 5, and then 7. Okay? And so then when I do that graph, make that a little smaller. So when I plot those points, then I go from the origin, this ordered pair here, which is -2, -1, means I go to the left 2 and down 1, and there's my first point. Then I go to the left 1 and up 1. I go neither left nor right, and then up 3. And then over 1 and up 5. And then over 2 and up 7. And then my function, of course, is not just those few points. My function is every point that exists on that line that contains those points. So the graph is a complete solution of that function. It shows you every value for x and what its y would be to go with it. And then you can try that for yourself on page 120 to check point 5. Now, the sixth objective, and remember we've only got 9, so this is almost over. On the sixth objective, we talk about using the vertical line test to identify functions. And then we have the definition here, or the explanation. The vertical line test for function means that if there's any vertical line and it intersects a graph in more than one point, the graph does not define y as a function of x. Because if you stop and think about what's going on there, if I have a graph, and I draw a vertical line. The x value of this point where the line intersects the graph and the x value of this point where it intersects the graph is the same x value, but it has two different y values. Therefore, this is not a function. Just a nice graphical representation of what we've already said, that for something to be a function, each x value can only have one unique y value associated with it. So things that would be a function would be maybe, I remember a parabola. If you have a parabola, as you can see, the vertical lines that you could draw through here only will touch once. And so that's an example of what it looks like for it to be a function. So try that for yourself on page 121 with checkpoint number 6. All right, objective 7 says we're going to obtain information from a graph. So if I have a graph and I've already drawn this graph on here, let's say I'm just going to draw myself a picture of something that's going on here. So we've got this kind of thing going on. We've done some kind of experiment. We've plotted these points, and this is the shape we get. There are some things that we can get or understand from this particular graph. We can find, so let's see, part A. Let's find out what f of 4 is. F of 4. Well, what does this mean? The 4 inside the parentheses means that x is 4. So that means on this graph I'm going to go over 4 units, and it wants to know what y value is associated with that. So it means I've gone up 2. So f of 4 is 2. They can also ask you, instead of doing it that way, they can ask you f of x is equal to 5 for what x value. And so if you look there, then what you do is you go up 5 units, and then you go across on this graph to find the place where it's actually 5 units, and so that is 2. And it's also what else? 1, 2, 3, 4, 5, 6, 7, 8, 9. Can you see here at 9? It comes back up and it goes up to 5 again. So you can just answer lots of questions by looking at this and understanding that every point on this graph is an ordered pair. This point is the point 2, 5. This point is the point 4, 2. This point is 0, 3. And you can answer questions based off that. Not only do they want you to be able to look at it and just get ordered pairs off of there, they also want you, and then you can do an example of that on page 123. We've got checkpoint 7. All right. Now, objective 8, like I say, not only can I get points off of it, but I can also look at any graph and be able to find the domain and range of the function by looking at its graph. And so I've just got us here some different graphs here, and we just need to kind of, just kind of do some different pictures with that. And then we'll just do this one. And this thing. All right. Now, when I drew this, I tried to be careful so that you could see the difference. Some of these have closed endpoints, and some of them have open endpoints. On example A here, both endpoints are closed. And what we're going to use in this book and throughout this course is what we call interval notation. But I want to kind of show you how it matches up to the set builder notation that you're probably used to from Algebra 2. When we do the set builder notation, when we talk about the domain here, this is all of the x's such that, now the x's live between -4, so it starts at -4, and that's less than or equal to, because it is actually closed, and up until 1, 2, 3, 4, 5. Okay? So here's how we did it before. We said the x's live from -4 to +5 in this domain. The range is the set of all y's such that they start at 0. Again, they're closed circles, so I use the equal to bar. And they go all the way up to 1, 2, 3, 4, 5, 6. Okay? So that's how you do it with set builder notation. Hopefully you're going to like the interval notation. With interval notation, we get to leave out all of that extra wordy stuff or extra symbols. You use a square bracket since it's an equal to, since it's a closed circle and you can actually touch that point. And for the domain, I go from -4 to 5. And you put a comma between the two so that you know that you're going, it's all of the numbers from -4 all the way up to 5. So your domain is written this way in interval notation. And then your range would be written from 0 to 6. A lot less. And so a lot of us like the interval notation a lot better, and it's used throughout this book. Now, on the set builder notation for the example B, this one I want you to notice it doesn't have the endpoints that are closed in. They're both open. So on my domain, I've got all the x's such that x lives between -4 and 1, 2, 3, 4, 5, 6, +6. So from -4 to +6. But please notice this time that I can't put the equal to bars underneath. It's just less than and not equal to because of the open circles. Now on the range, remember the range is talking about the y values, how far up and down. It's all the y's such that, now I start at -2, that's my lowest value, and it can't be equal to -2 because they're both open. But look at the top here. This goes all the way up to 3, but I'm actually got a solid line through 3, so it's less than or equal to 3. So when you use this interval notation, you got this domain would be from -4 to +6 with open parentheses around each one because we don't actually touch them. And then the range is from -2, and again, remember I use the open parentheses, comma, 3. But at the 3, I use the closed bracket because I can actually touch 3. It's actually a solid line. Example C here is a line with arrows at the end of it. That means what? Does anybody remember? That means that we can go on forever and ever. It doesn't have an end point. So here, this is, for the set builder, the domain is all real x's. So it's the set of x's such that x is an element of the real numbers. And the range is the set of all y's such that y is an element of the real numbers. So in interval notation, what that says is I'm going to go left forever to a negative infinity and right forever to a positive infinity. So in interval notation, I'm going from a negative infinity to a positive infinity for my domain and for my range both. Then on the set builder notation on the very last example C, here on my x values, I have x's such that, now I want you to notice that the bottom one here is supposed to be open, the top one's supposed to be closed. So I'm going from -4, and it's less than x, and it's less than or equal to 1, 2, 3, 4, 5, 6. And then on my range, I've got all the y's, such that that goes from 1, 2, 3, 4, -4, again, just to less than, up to 1, 2, 3, 4, 5. Okay, and that's actually equal to 5. So on this one, for the domain, we're going from -4 to 6, and from -4 to 5 on the range. Okay, so lots of examples. You try it now. If you will look in your book on page 125, there's checkpoint 8. And then we have one last objective, and we're through with this section. So we've got objective 9. We talk about x-intercepts and y-intercepts and zeros of functions. So let's just very quickly remind ourselves that x-intercept is the place where the graph crosses the x-axis. And the y-intercept is the place where the graph crosses the y-axis. It's just that easy. Now, the only part I've ever seen anybody having trouble is sometimes they forget that this one's the x-axis and this one's the y-axis. If you can remember that, you're in good shape. Now, I want you to notice if I draw a graph on here, that this point, and this point are all x-intercepts because I have crossed the x-axis with all 3 points. So my x-intercepts, let me spell that right, for this example are the points -4, 0, +5, 0, and 8, 0. Okay, so that's my set of x-intercepts. And then my y-intercepts is this point here, which is 0, 5. Now, if it talks about a zero of a function, what that's talking about is when the function value is 0. Let's think about that another way. What letter did the function value represent for us? That was when y was equal to 0. So in these, if you'll look, the x-intercepts always have a y value of 0. So zeros of functions and x-intercepts are the exact same thing. So zeros of functions and x-intercepts mean the same thing. And that's a really huge idea, and you need to remind yourself of that, and you need to memorize that. Okay? That finishes this section. This assignment starts on page 125. and you're going to do 5 through 115, the multiples of 5. So for those of you who aren't used to that, then what we're talking about here is you want to do 5, 10, 15, 20. You only do this the numbers of the problems that are multiples of 5.